The purpose of today's lab is to find the acceleration of a cart as it rolls down an incline. We know that a cart on a horizontal surface that we did in the last lab will go at a constant velocity, which gives us a straight line on a position time graph. We know that if we put a cart on an incline, it should speed up as it goes down the hill, so we should see a position versus time graph with an increasing slope, a curved line sloping upwards. So the problem, or the purpose, is to find the acceleration, the specific acceleration of that toy car as it rolls down the incline. Now, of course, we always phrase a problem in the form of a question. So take what I just said and rephrase it in the form of a question. What are we going to use to do this activity? Well, we're going to use materials that are similar to what you used in your first activity, that is your constant velocity lab. A little bit different, though. We're going to start off with the dynamics cart. The dynamics cart is going to be different than the toy car that you used the last time because it was motorized. This one isn't. This is just a toy cart that will roll on its own down an incline. You're also going to use a track. Some of you are going to use a metal track. Some of you are using a wooden track. Not a big deal. Just pick a track. The track that goes along with the cart that you chose. You'll see what I mean by that. The wheels for these carts that look like this are really, really narrow, and they fit in the grooves in the metal track. The wheels for the other carts are wider, and they fit in the grooves for the wooden track. But you'll see when I pull the apparatus out here what I mean by that. Now, you're also going to need something to block up this track. In other words, to create an incline. So maybe it's books or whatever. It doesn't really matter what you use. I'll just say books and star that because you may use something other than books to block that up to create the incline. Of course, you're also going to need your motion sensor. This is what you used last time when you did your constant velocity lab. You're going to use your air link, which is that device that's connected by a wire to your motion sensor. And then you're going to use your phone, which is going to be where you actually view your data. The data gets transmitted via Bluetooth from the air link to your phone. You're going to see a real-time graph of that data on your phone. And then, of course, ultimately, you're going to export that data to your Google Drive, share it with your partners, create a copy. Remember, that's what you do, is you always create a copy of the data before you do anything with it, and then do your thing. And you'll see exactly what your thing is in the next few minutes as we go through this. So that's the materials. Sometimes people might want to take a picture of the materials here and then insert that into your lab. Sometimes that's useful for helping you remember some of the materials so you don't forget one of them. Okay, but it's also useful in illustrating to the reader maybe a little bit better than just a list of the materials, what exactly it is that you use. Whatever, it doesn't really matter, as long as you have things labeled, okay, the words in there, okay, if you have the picture, that's just a bonus, all right? What comes next? Well, your procedure. I'm not going to give you the steps of the procedure, but I will briefly outline what you're going to do, and then you can write up your own little procedure. Basically, it comes down to this, okay? You're going to connect your phone to the air link so that you can view the data from the motion sensor on your phone. You're going to create an incline from the track by putting some books or whatever underneath one end. You're going to set up the motion sensor at one end, put the cart down on the track, turn on the motion sensor with your phone, and then let it go. That's it. That's all you're going to do. Press stop. When it gets to the bottom, I guess you got to press stop to stop collecting the data, right? Export it to your Google Drive and then do your analysis. So basically it's create an incline, put the cart on the incline, press start, let it go, press stop, export your data to your Google Drive and do your thing. Now, when you export your data to your Google Drive and then import it to Google Sheets, which is ultimately what you're going to do here because you're going to have to plot some graphs, you're going to see a few columns. Okay? 3 of those columns are time, position, and velocity. I want you to delete all of the other columns. If there's 4 or 5 columns, delete the extra ones, the extraneous ones, the ones that are not time, position, and velocity. From this data, time, position, and velocity, I want you to create 2 graphs. The first graph that I want you to create is a position versus time graph. The points on that position time graph should look something like this. I want you to plot a trend line that fits that data best. Then I want you to create another graph, which is velocity versus time graph. What do you think the graph should look like here? What shape should it be? Velocity time graph as this car accelerates going down the hill. Yep. No. Yeah, it should just be a straight line slope, right? Should look something like this. For this one, you're going to display the equation. Okay, you display the equation up in the top right-hand corner, which is going to give you the slope of that graph. Then answer the two questions. Describe the motion of the object using the position time graph, referencing the shape of the graph. What do I mean by that? Well, take a look at the position time graph and say, oh, the object is going at a constant velocity. I know this because the shape of the graph, blah, blah, blah. Or it's accelerating. I know this because the shape of the graph, so on. Or it's decelerating, slowing down. I know this because of whatever shape of the graph. Then question number 2 says, display the equation on your velocity time graph, right here. Identify which of the numbers in the equation represents the acceleration of the object. So when you show the equation here, there's going to be an equation that looks, depends on your numbers, right? But might be something like this, 3.45x plus 0.004. Okay, display the equation. And then identify which of these numbers, the 3.45 in my case, or the 0.04 in my case, identifies or represents the acceleration of the object. Your conclusion? Well, your problem, remember, was essentially to find the acceleration of this cart as it rolled down the incline. So the conclusion is the acceleration of the cart as it rolls down the incline is blank. Okay, what is the acceleration? Write down what the number is. And then how do you know? Then you got to get this, because this pretty much tells you, right? How do you know? Well, it's because of whatever number on that graph it was that gave you the acceleration of it. And then, of course, your sources of error. We always want to list 2 or 3 good sources of error, and then suggestions for improvement. What I mean by that is what with the materials could have led to a number for the velocity, for the acceleration of the toy car that wasn't quite accurate. Or maybe something with the procedure that led to something that wasn't quite accurate. Or maybe it's something with the management of your time. Or maybe it's something with just something with the surroundings. Okay, anything other than human error. Okay, don't list human error. Don't say we made a mistake while we were doing this. If you made a mistake while doing this, then fix it. Okay, don't list that as a source of error. Okay, sources of error are things that aren't your fault. Got it? Things that aren't your fault. Now, you also have to list suggestions for improvement. So, 2 or 3 good sources of error, plus what could you do to make it better? How could you improve that source of error? So for instance, if the wheel of your car wasn't turning very well, it was kind of getting stuck, what could you do to improve it? Well, maybe you could lubricate the wheel so that it would roll better. Right? Make sense? Don't say, I hooked up the motion sensor incorrectly. Well, then fix it. Don't tell me you hooked it up wrong. Just hook it up right. Sources of error are not human errors. They're things that are not your fault. Now, having said that, these suggestions for improvement, sometimes people spot a source of error as they're doing a lab. And then they say, oh, I'm not going to fix that because I want to save this source of error. I don't want to fix it because if I fix it, then I have to think of another source of error to list in your lab. You know what? My take on it is this. If you identify something that could be better partway through and you fix it, that's better than identifying after the fact and saying, oh, I'll fix it for next time, right? So if you find something partway through and you fix it, you can still list that as a source of error. And instead of saying, well, this is what I would do to fix it. Say, this is what I did to fix it. Make sense? So if you spot something, even better if you actually fix it today rather than just say, this is how I'll fix it for next time.